Welcome, everyone. Today, we'll discuss about another component of AI, that is neural networks. By the end of this video, we will be able to understand what is neural network, importance in AI and ML, its evolution, its basic concepts, and what are the different types of neural network. Also, we will discuss about its training process, including its applications and challenges. Lastly, we will see future of neural networks. Let's start by understanding what neural networks are. Imagine a network inspired by how our brains work. That's what neural networks are, a collection of interconnected nodes, or neurons, that work together to process information and make decisions. Think of these neurons as tiny processing units that receive input, do some calculations, and pass the result to the next neuron in line. Now, a neural network isn't just a random collection of neurons. It's structured into layers. You have an input layer that takes in data, one or more hidden layers that process this data, and finally, an output layer that gives us the result. Why are neural networks so important in the world of artificial intelligence and machine learning? Well, they have revolutionized these fields, allowing machines to perform complex tasks with incredible accuracy. Take pattern recognition, for example. Neural networks are exceptionally good at identifying patterns in data, whether it's recognizing faces in photos, understanding spoken language, or even predicting stock prices. This ability to learn from data and improve over time makes them invaluable. Think about autonomous systems, like self-driving cars or drones. Neural networks enable these machines to navigate and make decisions on their own, adapting to their environment in real time. In healthcare, neural networks are helping doctors diagnose diseases by analyzing medical images and patient data. They can spot patterns and anomalies that might be missed by the human eye. They are also key in natural language processing, powering language translation, sentiment analysis, and chatbots, making machines understand and respond to human language more naturally. Industries are being transformed by neural networks. In healthcare, they are improving diagnostic accuracy. In finance, they are detecting fraud and trading stocks. In retail, they are personalizing recommendations. To visualize this, imagine a simple diagram of a neural network with an input layer, some hidden layers, and an output layer. And think about all the different applications, like recognizing images, driving cars, and talking to virtual assistants. Neural networks are the backbone of modern AI and machine learning. Their ability to process and analyze complex data makes them powerful tools, driving innovation and efficiency across various industries. To truly appreciate the power and potential of neural networks, it's helpful to understand their history. Let's take a journey through time to see how neural networks have evolved. In 1943, Warren McCulloch and Walter Pitts introduced the McCulloch-Pitts neuron. It was a simple model using binary inputs and outputs, laying the foundation for neural network development. Jump to 1958, and we have Frank Rosenblatt's perceptron. It could learn from data and recognize patterns, but had its limitations with complex problems. Then, in 1986, the backpropagation algorithm by Rumelhart, Hinton, and Williams changed everything. It allowed multilayer networks to adjust and learn from errors, making them much more powerful. Today, deep learning has taken neural networks to new heights. With many layers, these networks excel in tasks like image and speech recognition. Reinforcement learning is another exciting area. Here, networks learn by receiving rewards or penalties, mastering complex games and tasks. To sum up, the history of neural networks is a fascinating journey from simple models of brain function to powerful tools that drive many of today's AI applications. Now, let's dive into some basic concepts of neural networks to understand how they work. First, let's talk about neurons and layers. Think of a neuron as a tiny unit that takes an input, processes it, and passes the output to the next neuron. A neural network is made up of many such neurons organized into layers. These layers include: first, we have the input layer. This is where the neural network receives the initial data. Think of it as the starting point where raw data, like images, text, or numerical values, enters the network. Each neuron in the input layer represents a feature or dimension of the data. Next, let's talk about hidden layers. These are the layers where all the magic happens. A neural network can have one or many hidden layers, depending on its complexity. Each hidden layer consists of neurons that take inputs from the previous layer, process them, and pass the results to the next layer. Hidden layers allow the network to learn intricate patterns and representations of the data. The more hidden layers, the deeper the network, and generally, the more complex the patterns it can learn. Finally, we have the output layer. This is the last layer in the network, and it produces the final result, such as a classification label or a predicted value. The structure of the output layer depends on the type of problem being solved. For example, in a binary classification problem, the output layer might have a single neuron with a sigmoid activation function to output a probability. Next, we have activation functions. These functions determine how the input signal is transformed as it passes through a neuron. They add nonlinearity to the network, allowing it to learn and model complex data. Let's discuss weights and biases. As you can see in the picture, in a neural network, each connection between neurons has a weight, which adjusts as the network learns. These weights determine the importance of the input features in predicting the output. Biases are additional parameters in each neuron that allow the activation function to be shifted to the left or right. They help the network fit the data better by providing additional flexibility. Imagine weights and biases as tuning knobs that the network adjusts during training to minimize errors and improve accuracy. Next, we have activation functions. These functions determine how the input signal is transformed as it passes through a neuron. They add nonlinearity to the network, allowing it to learn and model complex data. Some common activation functions include sigmoid. This function outputs values between 0 and 1, making it useful for binary classification. Tan, similar to the sigmoid but outputs values between -1 and 1, often leading to better convergence. ReLU, rectified linear unit. The most popular activation function, which outputs the input directly if positive, otherwise, it outputs 0. It helps in avoiding the vanishing gradient problem and speeds up training. Lastly, let's discuss weights and biases. In a neural network, each connection between neurons has a weight, which adjusts as the network learns. These weights determine the importance of the input features in predicting the output. Biases are additional parameters in each neuron that allow the activation function to be shifted to the left or right. They help the network fit the data better by providing additional flexibility. Imagine weights and biases as tuning knobs that the network adjusts during training to minimize errors and improve accuracy. The basic concepts of neural networks include neurons organized into layers, activation functions that introduce nonlinearity, and weights and biases that the network learns and adjusts. Together, these elements enable neural networks to learn from data and make predictions. Neural networks come in various types, each suited for different tasks. Let's explore some of the most common types of neural networks. First, we have feed-forward neural networks. These are the simplest type of neural networks, where data flows in one direction, from the input layer, through the hidden layers, to the output layer. They are used for tasks like image and speech recognition, where the relationship between input and output is straightforward. Next, we have convolutional neural networks, or CNNs. CNNs are designed to process data with a grid-like topology, such as images. They use convolutional layers to automatically and adaptively learn spatial hierarchies of features, making them highly effective for image recognition, object detection, and even video analysis. Then comes recurrent neural networks, or RNNs, are designed for sequential data. Unlike feed-forward networks, RNNs have loops that allow them to maintain a memory of previous inputs. This makes them ideal for tasks like time series forecasting, language modeling, and speech recognition. Next comes generative adversarial networks, or GANs, a unique type of neural network used for generating new data. A GAN consists of two networks, a generator and a discriminator, that compete against each other. The generator creates fake data, and the discriminator tries to distinguish it from real data. Lastly, we have autoencoders. These are a type of neural network used for unsupervised learning tasks like data compression and anomaly detection. An autoencoder consists of an encoder and a decoder. The encoder compresses the input into a lower dimensional representation, and the decoder reconstructs the original input from this compressed form. Now that we understand the architecture of neural networks, let's delve into how they are trained to perform specific tasks. Before feeding data into a neural network, it's crucial to pre-process it. This involves tasks like normalizing the data to a standard scale, handling missing values, and encoding categorical variables. Data preprocessing ensures that the network can learn effectively from the input data without being biased or misled by irrelevant information. Once the data is preprocessed, it's time for forward propagation. This is the process by which the input data flows through the network, layer by layer, to produce an output. Each neuron in the network receives input from the previous layer, applies a set of weights and biases, and passes the result to the next layer through an activation function. Now, let's talk about backpropagation and gradient descent. After the network generates an output, we compare it to the actual target value using a loss function. This loss function quantifies how far off the predictions are from the true values. Backpropagation is the process of propagating this error backward through the network, layer by layer, to update the network's parameters, such as weights and biases, so as to minimize the loss. This is done using the gradient of the loss function with respect to each parameter, computed using the chain rule of calculus. Gradient descent is the optimization algorithm used to adjust the parameters in the direction that reduces the loss. It involves taking small steps down the gradient of the loss function until reaching a minimum. Finally, let's address overfitting and regularization techniques. Overfitting occurs when a model learns to memorize the training data instead of generalizing to unseen data. This often happens when the model is too complex relative to the amount of training data available. To prevent overfitting, regularization techniques are employed. These include methods like L1 and L2 regularization, dropout, and early stopping. Regularization adds constraints to the network's parameters, discouraging overly complex models and promoting better generalization. Now, let's explore the wide range of applications where neural networks are making a significant impact. Neural networks, particularly CNNs, excel at identifying objects, people, and scenes within images. They power facial recognition, autonomous vehicles, medical imaging analysis, and social media photo tagging. It enables language translation, sentiment analysis, chatbots, and virtual assistants. INNs and transformer models revolutionize NLP by capturing context and semantics for more human-like interactions. Speech recognition technology, driven by neural networks, enables accurate transcriptions and powers voice-controlled assistants like Siri and Alexa. It's also used in automated transcription and voice search. Deep reinforcement learning algorithms learn to play games at superhuman levels by interacting with the environment. They've mastered games like Go, chess, and video games, and are applied to real-world control tasks. Neural networks analyze medical images to detect diseases like cancer, predict patient outcomes, and optimize hospital operations. They improve diagnostics, treatment plans, and patient outcomes. Neural networks power diverse applications, from image recognition and NLP to healthcare and game playing, revolutionizing how we interact with technology and solve complex problems. While neural networks offer immense potential, they also come with challenges and limitations that need to be addressed. One significant challenge is the computational cost of training and running neural networks, especially deep neural networks with many layers and parameters. Training complex models requires substantial computational resources, including high-performance GPUs or even specialized hardware like TPUs. This can be a barrier for individuals and organizations with limited resources. Another challenge is the extensive data requirements for training neural networks effectively. Deep learning models, in particular, thrive on large volumes of labeled data to learn meaningful patterns and make accurate predictions. Acquiring and annotating such datasets can be time-consuming, expensive, and sometimes impractical, especially for niche domains or rare events. Neural networks, especially deep neural networks, are often regarded as black box models because they lack interpretability and explainability. Understanding how these models arrive at their predictions or decisions can be challenging, making it difficult to trust or validate their outputs. Ethical considerations also pose significant challenges in the use of neural networks. Biases present in training data can propagate and amplify in the model's predictions, leading to unfair or discriminatory outcomes. Additionally, the increasing automation enabled by neural networks raises concerns about job displacement, privacy infringement, and potential misuse of AI technology. Addressing these ethical concerns requires careful attention to data collection, model development, and deployment practices. As we look ahead, the future of neural networks holds exciting possibilities and transformative potential. One area of ongoing research is the development of more efficient and scalable neural network architectures. Researchers are exploring techniques like sparsity, weight sharing, and neural architecture search to reduce computational costs and improve performance, making neural networks more accessible and applicable to a wider range of tasks. Another area of interest is in advancing interpretability and explainability in neural networks. Researchers are developing techniques to make these models more transparent and understandable, enabling users to trust and validate their decisions in critical applications like healthcare, finance, and autonomous systems. The future may also bring breakthroughs in areas like lifelong learning and meta-learning, where neural networks can continuously adapt and learn from new experiences without forgetting previous knowledge. Advancements in neuro-inspired computing, such as neuromorphic hardware and brain-computer interfaces, hold promise for bridging the gap between artificial and biological intelligence. Overall, neural networks will continue to drive innovation and transformation across various sectors, revolutionizing how we work, live, and interact with technology. Let's check your understanding based on the concepts covered in the video. First question is: what is the primary function of activation functions in neural networks? You can hit the pause button and try answering it on your own. The correct answer is option C. To introduce nonlinearity. Next question is: which type of neural network is specifically designed for processing sequential data like text and time series? You can hit the pause button and try answering it on your own. The correct answer is option B, recurrent neural networks, RNNs. Let us do a quick recall of what we have covered in the video. We've explored the fascinating world of neural networks. We began by understanding the fundamental concepts of neural networks. We then delved into various types of neural networks, such as feed-forward networks, CNNs, INNs, GANs, and autoencoders, each with its unique applications. We discussed the challenges and limitations faced by neural networks, such as computational costs, data requirements, interpretability issues, and ethical considerations. Looking ahead, we highlighted ongoing research areas, potential breakthroughs, and the profound impact of neural networks on industries and society. As we conclude, it's evident that neural networks hold immense promise and potential to drive innovation and transformation across various domains. That was all for this session. We will dive deep into the other concepts in the upcoming videos. Thank you.